So in our basic introduction to rotational mechanics last time, we had understood few things like the difference between pure translation and pure rotation of a rigid body. Okay, so in rigid body motion, we have seen that, for example, when we compare pure translation with pure rotation, main thing we understand is in pure translation, a rigid body is moving in such a way, okay, that if you compare the instantaneous velocity of the center of mass, it is equal to the instantaneous velocity of any other point. Okay. So therefore, all the particles of the rigid body have identical motion. If they have instantaneous velocity which is identical, then obviously, so any arbitrary point within the rigid body or any arbitrary particle within the rigid body, okay, has the identical instantaneous velocity as the center of mass. So it means obviously their displacements after some time will be identical. Their instantaneous accelerations are identical. And therefore, we also saw that the entire kinetic energy of a rigid body like this is simply defined as this. Okay. Half of total mass into instantaneous velocity of center of mass, which is the same thing as velocity of the entire body. So that was the defining factor about pure translation. Okay. Similarly, the defining, or I mean, rather not similarly, but contrastingly, the defining part about pure rotation is that it is rotation about a fixed axis. So whenever we attach the term pure with rotation, it means we are talking about rotation about a fixed axis. Okay. So the moment we are looking at rotation about a fixed axis, it is the rotational motion which is common to all the particles, whereas the individual velocities, accelerations, etc., they need not be identical. In fact, they will not be identical. So if we compare, let's say, an arbitrary point P over here, its instantaneous velocity is like this, its instantaneous acceleration might be like this. Okay, and that is definitely not equal to those for another particle somewhere here, let's say. Say we have another particle P prime. So its velocity is different, both in magnitude as well as direction. Okay, but what is common is the circular motion part. So all particles are in circular motion, okay, about a common fixed axis. Okay, simultaneously with the same, etc. So angular parameters are common. And then from there on, we saw a very interesting result that if you look at the kinetic energy of an arbitrary particle, P, let's say, it is half of dm into, okay, so this is the kinetic energy of, so left hand side should be kinetic energy. Okay. So this is the kinetic energy of a particle, let's say P, of mass dm. Okay, where rp is nothing but the perpendicular distance of that particle, okay, with respect to the axis of rotation. So the total kinetic energy of the rigid body, when we calculate, that is now called the kinetic energy of rotation. It comes by integrating this quantity, and it becomes this expression, which is something new for us. Okay. But if we compare this equation with this, which is the kinetic energy of translation, we can see that now kinetic energy of rotation is proportional to omega square, whereas kinetic energy of translation was proportional to v square. But similarly, the inertia term, it is half into some inertia term into v square. Like that, it is half into some inertia term into omega square. So the inertia term is now a different quantity, and that is called the moment of inertia. Okay, or it is also called rotational inertia. Okay, and we saw that the formula as per the above integration for moment of inertia is integration r square dm over the entire mass of the body. So moment of inertia is a physical property of the rigid body with respect to the given axis of rotation, which has dimension of mass into length square. So it is a physical property of the rigid body in relation to the given axis. Okay, so it's in relation to the particular fixed axis. Okay, and it is about distribution of mass. With respect to the axis. Okay, so this was a new physical quantity that we learned about in context of rotation. Okay, and then we had derived the formula for moment of inertia of a thin rod, first about its perpendicular bisector, and then about an axis which is bisecting it, but at some general angle alpha with respect to the rod's length. Right? Okay, so hope we are clear up to this point. Okay.
Yes, sir.
Any questions about the concept of moment of inertia till this point? Okay.
Sir, I have a doubt to clarify.
Yeah, tell me.
Half omega I square is just the kinetic energy for the pure rotation, right?
It is the kinetic energy of the entire rigid body, okay, when it is in pure rotation.
Okay, sir, thank you.
Okay, about that fixed axis with an angular speed omega. Okay. So, one way to think about this is as an external agent, suppose, the rigid body was at rest initially and you make it translate with a velocity of VCM, then how much work you have to do? It's the amount of energy you have to give it, which it would be half mv square, right?
Yes, sir.
Now, like that, if we have a rigid body which has a fixed hinge or a fixed axis, like a door, which has a fixed axis at one end. Now, initially it is at rest, and now you want to set it moving with an angular speed omega, then how much work has to be done? So
Half
that
I
is equal to
omega
the
square.
kinetic energy. So that is half I omega. So now you can see that that work done depends on obviously the angular speed you want to give it, but it also depends on a particular physical property of that rigid body. And that physical property is not only about the mass, it is also about the distribution of mass. Right?
Yes, sir.
Okay. So let's look at a couple of more examples of calculation of moment of inertia. By application of definite integration. Okay, so some of these examples that we are doing are going to be standard examples, which you'll have to remember because we'll be using these values of moment of inertia directly in questions. Okay. So one of those standard examples we saw last time, the moment of inertia of a thin rod about its perpendicular bisector. Now, next example we'll see is again thin rod, but this time we'll take the axis of rotation perpendicular to the rod, but passing through one end. Okay. So if this is a thin uniform rod of mass m and length L, but this time we'll take the axis of rotation through one end of the rod and perpendicular to it. Okay, so if it is rotating like this, so the axis is perpendicular to its length, okay, and through one end of the rod. Okay, then tell me how much will be the moment of inertia. So this is a very simple derivation. Can you people try it? Okay. So use the same protocol that dm will be lambda dl because it's a linear distribution of mass. Okay. And now appropriately take the value of dl and r and do the integration. So it's effectively the same integration we saw last time, but only the limits of integration will change. Yes, very good. Answer is ml square by 3. And this is again one of the standard values of moment of inertia, which we will just keep in mind from this point. Okay, so same method, only the limits of integration. Suppose we take the distance of a particle on the rod from the axis as x. Okay, so at a perpendicular distance x from the axis of rotation, we are slicing a thin element of thickness dx. So the mass of that element Okay, that becomes m by L dx. And the perpendicular distance from the axis of rotation for that point becomes x. So x square into m by L dx integrated from 0 to L. So that's the only difference. So finally, this will give us ml square by 3. So now immediately, if you compare this with the result that we got that day, you can see that there is a difference, and it's quite a huge difference. When we took the axis about the center and perpendicular, we saw that the moment of inertia was how much? ml square by 12.
Yes, sir.
So that is like 1/4 of this. So why this huge difference in values of moment of inertia? Because the body is the same, but the distribution of mass with respect to the axis. When you take the axis as passing through the center, you can see that the distance of the different particles, okay, it's only ranging between 0 and L by 2. Okay, when you take this axis, okay, the maximum distance that any particle is at, it's only L by 2. So the moment of inertia is a lot less in comparison. It's ml square by 12. Whereas when we take the same body, but now the axis is through one end and perpendicular, you can see that the distance of the furthest particle is now L, so it's double. So the moment of inertia is becoming 4 times, becoming ml square by 3. Right, so let's move on to our next example of moment of inertia. Now, the next example is the simplest derivation of moment of inertia. In fact, it's almost like a statement of fact, it's not. So if we now have another linear body in the shape of a thin ring, thin uniform ring, okay, and we want to calculate moment of inertia about its symmetry axis. Okay, so the symmetry axis is the one passing through its center and perpendicular to its plane. Now, if we consider this as the axis of rotation, so why it's very simple is because every particle is at the common distance of capital R. So the moment of inertia, which is R square dm, this becomes common value of capital R for all the particles. So we have to just integrate over the entire mass. So the entire mass of the body is at a common distance of capital R from the axis of rotation. So the moment of inertia just becomes mr square. Right, this is clear, I hope.
Yes, sir.
Okay. Okay, now from this we move on to our next example, which is going to be our first instance of a surface distribution. So moment of inertia of a thin uniform disk now. Okay. Again about the symmetry axis. So now the disk is a surface distribution. In fact, it's a laminar surface lying on a two-dimensional plane. So we'll have to take dm as sigma dA. So what will be the logical way of slicing differential elements?
Into rings.
Yes, very good. Okay, because rings will have the same symmetry. So this is our disk. And but this is our axis passing through the center and perpendicular to its plane. Okay, so we will take our differential element as differential rings. So a ring of radius small r, let's say, okay, and thickness dr. The area of the ring, remember how much that will become from,
Pi r dr.
in this case 2 pi r dr, right? Because it's a full ring. So about this axis, if we take a ring of radius r and thickness dr, its area becomes length into thickness, so 2 pi r dr. So its mass will become sigma into dA. So sigma here will be how much? It's a uniform disk. So sigma will be total mass divided by area. Okay. So this will become 2m by capital R square into r dr. Okay. Now the moment of inertia of that ring, we'll just make use of the formula from above. So that ring's moment of inertia about the given axis, that is dm into r square. So that becomes 2m upon capital R square r cube pr. So now the moment of inertia of the disk is the moment of inertia of all the rings. Okay. So 0 to capital R.
So it seems like the moment of inertia of all bodies is like mr square into some k.
Yes, if it is a round object, like a ring or a disk, or we'll see later, we can have a hollow spherical shell, we can have a solid sphere. Okay, then it will be some numerical factor into mr square. And typically that numerical factor will be less than equal to 1. And you can understand logically why. The ring out of all of these has the maximum possible moment of inertia, because all the mass of the ring is the furthest away from the axis, which is capital R.
Yes, sir.
But in the case of the disk, or we'll see hollow shell or solid sphere or any of these, the mass is distributed between 0 and capital R. So the moment of inertia becomes less than mr square. It becomes some fractional part into mr square.
Right. Yes, sir. So any way of knowing that k, like from the shape only, we'll say okay, the k should be like this.
That way is the derivation using integration beta.
Okay, sir.
Okay, but that is where the application of integration becomes important, no? Because that factor depends on the distribution of mass, right?
Yes, sir.
And the only way you will get that distribution of mass is by integrating over the entire mass, no?
Yes, sir.
Okay.
So in the above one,
Yes.
why didn't we substitute dm?
There was no need to substitute dm, because you can see now what is in the integration when we are substituting small r as capital R, it's a
Yes.
constant now.
Yes.
So it's coming outside the integration. Okay.
Okay.
So
Yes.
we could have done that same thing, that we would have taken, DL as r d theta like we
Yes.
normally do for circle and all that. But that was unnecessary over here, right?
Yes. Okay.
So we just use that trick that, okay, we are just integrating dm over the entire mass. So it is, so you can, additionally write down one step here that integration dm is nothing but the total mass.
Yes.
So that's why we did not need to substitute dm as lambda dl or like that.
So done.
Okay, so how much is the answer coming for this, the disk?
mr square by 2 pi.
R square by 2.
Yes, so this is again a standard formula that you must remember. Moment of inertia of a disk about its symmetry axis. Now,
Sir, why is then there a pi, sir?
why should there be a pi? Tell me. Okay.
So because sigma is m square by pi r square, no? 2m by pi r square.
Yeah, but the radius of the disk, I mean the area of the disk also has a pi, no?
Right, yes, sir.
Okay. So I have just skipped one step over there. After substitution, that pi will cancel, right?
Yes, sir.
Okay.
1 second, sir.
Yeah. Now later when you are revising today's notes, as another exercise, what you can do is use integration to find moment of inertia of this disk about its diameter. About an axis which is along a diameter. So you can take the above diagram, you can take the vertical diameter or the horizontal diameter, whichever be the case. This. Okay. So we'll discuss about this result in the next lecture. You try this yourself.
Okay, sir.
Okay, now let's move on to our next standard derivation, which will be moment of inertia of a thin spherical shell about, again, a symmetry axis. Okay. Again, uniformly distributed mass. So the symmetry axis is along any diameter basically. So again, it's a surface distribution, but this time it's a non-laminar surface. So this is our axis of rotation. Now we have to understand that this is a three-dimensional surface, unlike the disk. Okay. So this mass is m and radius is r. So what should we take as our differential element again here?
So rings again?
Yes, again we will see, we'll take rings, okay, thin rings sliced by a plane perpendicular to the axis, those kind of rings. And sigma will be m upon 4 pi r square this time. So surface area of a sphere we had seen is 4 pi r square. We had proved that by integration also at one stage. Okay. So just try this out. Now, just remember the protocol that we do for integration over the surface of a sphere. Now, when we slice the rings, the thickness of the ring should be taken as a thickness on the curved surface. It's like you're taking ribbons of a certain thickness dl and you are wrapping them around the surface. So that dl lies on the spherical surface. The dl is not the thickness projected on this axis. It is the thickness that is on the surface. So it is always taken as r d theta, capital R d theta. Just try to settle this correctly yourself. I'll put it up in a minute. So let's just go over this. So our axis of rotation is, let's say, our y-axis. So we slice rings using a plane parallel to the xz plane. Okay, because the axis of rotation I have taken as the y-axis. Okay. So that being the case, our rings are going to look like this. Or this is one of the differential rings. So as usual, we will locate the ring by its angular position. Okay. So the angular position of the ring is, let's say, theta with respect to our x-axis. And the thickness of the ring, the small arc length dl, this will be subtending a small angle d theta. So this angle here, this is d theta. Now we can also see that the radius of the ring, small r, let's say. So a thin ring has a radius small r, which we can express as capital R cos theta, and it has a thickness. So this is the same thing that we've seen in center of mass. And in fact, we had used this to prove that the surface area of a sphere is 4 pi r square. So circumference into thickness. So now the important thing is that the mass of that ring become so it is m by 2 cos theta d theta. Okay. So if the mass of this thin ring is this much and its radius is this much, then the moment of inertia of that thin ring about our y-axis, that will be how much? That will be dm into r square. So m by 2 cos theta d theta into r cos theta whole square. So this is the moment of inertia of any of the differential rings. So now we have to figure out what is the moment of inertia of the whole disk by integrating this with the proper limits. Okay, so try the next step yourself.
So shouldn't dA be 2 pi r square cos square d theta?
No, small r is r cos theta, no? And dl is r d theta. So cos theta doesn't come with a square, beta. Isn't it?
So 2 pi r dr is equal to 2 pi
No,
r
no,
square.
2 by r dl, beta. Dl is the thickness, no? And the thickness is r d theta, no?
Yes, sir. Then sir, we get
But
2 pi r square d theta, right?
small r is capital R cos theta, beta. And dl is r d theta. So multiply these two.
R square cos, अच्छा capital R.
2 pi small r into dl, no? So now substitute small r and dl from above.
Yes, sir, I got it.
Okay, so now when I integrate, what should the limits of theta be?
Minus pi by 2 to pi by 2.
Yes, because the bottommost ring here at y equal to minus capital R will have an angular position of minus theta, the way I've taken theta. Okay. Whereas the topmost one at y equal to plus R will be at plus pi by 2. So integrating over all the rings, you'll have to take so this mr square by 2 comes outside, and we have cos cube theta d theta integrated from theta equal to minus pi by 2 to theta equal to plus pi by 2. Now, how do we go about this integration cos cube theta?
Sir, by taking it.
Sorry?
Sir,
Come again?
by substituting cos cube theta with cos 3 theta plus 3
Okay,
cos theta upon 4.
that's one method. Yes, we can do that using the formula of cos 3 theta, right? Okay. Anything else? Any other method we can use?
So cos cube theta is cos theta into cos square theta. So cos theta into 1 minus sine square theta.
Very
And if we
good.
substitute sine theta as t.
Correct. So we can express cos cube theta as a combination of sine theta and cos theta, right? So that
Yes,
is
sir.
probably an easier method at this stage. Okay. I mean, there's the formula based method also using the cos 3 theta, but probably the simpler method is this, that do this. Okay. And if you take, so integration cos cube theta becomes integration of 1 minus sine square theta, let's say, into cos theta d theta. Now the advantage of this is that cos theta is the derivative of sine theta, right? So we can substitute sine theta as z. So cos theta d theta becomes dz. So this integration becomes 1 minus z square dz, which becomes z minus z cube by 3, okay, which ultimately becomes sine theta minus sine cube theta by 3. Okay, so this integration is correct.
Yes, sir.
Okay, so now we'll just substitute the integration directly over here. So my moment of inertia will become mr square by 2 into the indefinite integration sine theta minus sine cube theta by 2, and on that we'll put the limits minus pi by 2 to pi by 2. So now substitute the limits and see what we're getting for moment of inertia. So upper limit is, sorry, sine cube theta by 3. So upper limit is 1 minus 1 by 3. So that's 2 by 3. And lower limit sine of minus pi by 2 is minus 1.
Sir, why are we getting mr square again?
Because again, no, the distribution of mass from the axis of rotation is between 0 and capital R. No? So it will obviously be some fractional number into mr square.
Sir, it shouldn't be equal to that of a ring, no?
No, beta, the distribution is different.
2 mr square by 3.
Yes, 2 by 3 mr square. Ring is very different, no? But a ring, all the mass is at a common distance of capital R from the axis of rotation. No? Here, imagine the spherical shell. Just imagine the particles which are like near the poles of that axis. They are hardly having any radius of curvature. No?
Sir, I'm saying the same. I got mr square, so I was saying, how is it equal to a ring?
Oh, you got the answer. Okay. No, so see, the upper limit will be 2 by 3, you know, when you put pi by 2, and the lower limit will be minus 2 by 3 when you put minus pi by 2. So the quantity from the integration that you're getting will be 2 by 3 minus of minus 2 by 3. That's 4 by 3, and you multiply it with mr square by 2. So the correct answer, yes, Ibrahim, that is 2 by 3 mr square. So again, this is a standard formula that we have to memorize, you know, for the moment of inertia of spherical shell, 2 by 3 mr square. Okay, so this kind of calculation we'll get. Okay, an axis coinciding with the diameter. Okay, so okay, so hope this example is clear to all of you.
Yes, sir.
Okay, now let's come to the last of the standard derivations. You might have guessed is the solid sphere, right, of uniform density. Okay, so that will also be some factor into mr square. Now, before we get into the calculation, just if I try to logically analyze, should the moment of inertia of a solid sphere of mass m and radius r, if I compare it with the hollow spherical shell of same mass and radius, should the solid sphere have a larger or smaller moment of inertia?
Smaller.
Can we be sure about that? I mean, it's obvious.
Yes, sir.
Okay, good. Of uniform density. So again, moment of inertia about a diameter axis, any axis passing through its center. Okay. So this is in fact our first example of a volume distribution. We'll see other volume distributions also, but mostly we will not have to use integration because we'll use a couple of theorems, okay, and the standard formula, and from that we'll be able to. So again, this is a three-dimensional object, but this time it is solid. So its mass m and radius r means it has a density of m upon 4/3 by r cube. Okay. So let's say this is the axis we are talking about now, passing through the center. So how should we slice our volume elements now?
So we slice it into shells.
So discs.
Yeah, we can do both. We can slice into discs, okay, by slicing using a plane parallel to the, perpendicular to the axis. Or we can now do one other thing. We can think of the solid sphere like, the layers of an onion. It's shell after shell placed concentrically on top of each other. So that way we can take advantage of the formula we've just derived earlier. Okay, so that is a more simple way of going about the integration. So here dm, when we take it as rho dv, so what we will go with over here is we will take this as the thin shell of radius small r and thickness dr, but you can also slice it into discs, okay, and you can try that later as an integration exercise and you'll see you'll get the same result. So if I take a thin shell of radius r and thickness dr, what should be the volume of that shell dv?
Area into thickness.
Yes, surface area into thickness. So that will be 4 pi r square into dr. So that is also a way to, for example, if you want to derive the formula of volume of a sphere, you can always take it that way. Okay. Integrate for the volume of the shells. So now I've taken a shell of radius r and thickness dr. So the volume of this shell is surface area into thickness. Okay. That's how you can get volume of a sphere by integrating dv. 0 to capital R. This is one way of proving that the formula for volume is 4 by 3 pi r cube. We've seen this before also, I think. Okay. So anyway, now this shell has a mass which will become this. Okay. That is our density into volume of the shell. Just simplifying this a little, 3m upon r cube into r squared dr. That is the mass of the shell. So now for that differential shell, what will be the moment of inertia? It will be 2 by 3 dm into r square using the formula of shell that we've just derived above. Okay. So moment of inertia of a thin hollow spherical shell was 2 by 3 mr square. So now we're talking about a differential shell. So its mass is dm and its radius is small r. So its moment of inertia about the same diameter axis will be its mass into its radius square into the factor 2 by 3. Okay. So now just integrate. Okay. So I for the sphere, the solid sphere, will become integration of di for all the shells. Okay, so very simple integration. Just finish this now.
The 2 by 5 mr square.
2 by 5 mr square. Very good. That's correct.
So can you explain again why it's 2 by 3?
Which one? This
Or
di
di
of the
equal-
shell.
Yes, sir.
So thin spherical shell, no, we have derived moment of inertia of a shell of mass m and radius r is 2 by 3 capital M r square. No?
Yes, sir.
So now instead of a shell, it's a differential shell. So its mass is dm and its radius is small r. But that shell has how much moment of inertia about this axis? 2 by 3 of its mass into r square. No?
Oh, okay, sir. Yes.
Understood? Okay. Okay, so on substitution, this will become integration of 2 by 3 dm into r square. Okay, and then we'll substitute dm as this. Okay. So finally, you'll see you'll get an r to the power 4 r dr kind of integration. Okay. That's how the factor of 5 in the denominator will come. So 2 by 3, now dm is 3 capital M by r cube into r square dr into r square. So that's how we get this. So we get 2m by r cube the constant factor, r to the power 4 dr, and obviously from the center to the outer circumference. So finally our answer becomes 2 by 5 mr square. Okay. Okay. So thin rod, okay, thin disc, thin ring, then thin disc, then thin spherical shell, and solid sphere. Okay, these are 5 of the very fundamental formulae that you must remember for moment of inertia. Okay, so apart from the rod, which has a length L, so moment of inertia depends on ml square. The others all have some kind of radius. They have a round sort of distribution. So the moment of inertia has always some factor into mr square. Okay, so this is the basics of moment of inertia. Okay, now there are a few more things also we'll learn about moment of inertia, including some theorems of how to find moment of inertia or how to compare the moment of inertia about two different axes for the same body. Okay, and some other examples also, but those will come to after some time. Now, next thing I want to do is we want to learn a little bit about the basics about other factors related to or other aspects of pure rotation. Okay, obviously moment of inertia is one property which is related to the rotation of a rigid body about a given axis, and that is a physical property of the body which has to do with mass distribution. And so far we have seen what is the application of moment of inertia. It comes into application when we are calculating the kinetic energy. So if we know the angular speed of the rigid body about its given axis, then we can calculate the kinetic energy using the moment of inertia. But as I told you before, that is not the only application. Okay, moment of inertia is significant in the entire dynamics of the rigid body. So let's understand few more of these things. Okay. So going back to the basics, yeah. Tell me, Beta.
Could you please scroll up? I was actually noting it down.
Yeah. Right. So now we will go back to pure rotation of a rigid body and understand a few more properties of pure rotation. So for that, we will start with kinematics of pure rotation, okay, which is very similar to kinematics of circular motion, but with some additional things. Okay, done with this now?
Just a second, sir. Almost done.
Okay. Okay, done now?
Yes, sir.
Okay. Achha, one more thing about moment of inertia. Instead of a continuous distribution of mass like a rigid body, if we have a system that consists of discrete particles, but they are connected rigidly to each other. Okay. So moment of inertia of a discrete particle system So if we have individual particles M1, M2, M3 in some kind of a structure. Okay. So I'll give you an example or two to understand this. Okay. And these are all rotating about some axis like this. So this system, okay, that consists of these individual particles. Okay. So if the individual particles are at perpendicular distance R1, R2, and so on and so forth, then the moment of inertia, instead of integration, we just now have summation of for all the particles. Okay, so you can see, for example, suppose I have a square frame made of massless rods or very light rods, and at the four corners of the square frame, I have four particles. Okay. And let's just say for variety that these two particles are of mass m, and these two particles are of mass 2m, and these are light but rigid rods of length L each. Now we want to find the moment of inertia of this system about this axis, the axis that lies in the plane of the square but bisects two of the sides. In terms of M and L, we want to find the moment of inertia. So in such a case, we will use the above formula because our system has its mass distributed into individual discrete particles instead of continuously. Yes, 5 by 2 ml square. Why 5 by 2? 3 by 2, yes. Should be 3 by 2 ml square. Okay. Okay, so each of the particles is at a perpendicular distance of L by 2 only. Okay, so when we do summation mr square, we'll just get, so in this case, it will be m plus 2m plus m plus 2m. All four particles are at a common distance L by 2 from the axis. So that's how you'll get 3 by 2 ml square as a moment of inertia. Okay, now from this we will move on to kinematics of pure rotation.
1 second. Sir, a bit more.
Sorry, come again?
Sir, can you scroll up for 1 second?
Yeah.
So I was thinking of other methods to do this. We can also condense them right together, like 3m of one and 3m of the other at a distance L by
Yes.
2 axis.
In this case, you can do that because all of them are having the same distance from the axis of rotation.
Yes, sir. But another thing is we could have also found the comp for m and 2m.
No,
and
so that is where I'll explain something. In discrete particle system or even in continuous mass distribution, don't use the concept of COM because they're different things. COM is, no, it is based on the weighted mean of the mass distribution, right?
Yes, sir.
Whereas moment of inertia depends on the mass distribution in terms of r square.
Not r. Okay, sir.
Not
Okay.
r. So not vector r, but r square. So for example, if you condense a solid sphere, its mass, center of mass is located at the geometrical center, no? Centroid. So then about the diameter axis, okay. So you cannot compare the moment of inertia of a solid sphere about its diameter with the equivalent particle of same mass located at its center of mass. Okay, because the distribution of mass is not the same for the two things.
Yes, sir.
Okay.
Sir, I'm done. Thank you.
Okay. Okay. Now coming to kinematics of pure rotation. So we have a rigid body of mass m, which is rotating about, let's say, this fixed axis. Okay. So we obviously have the concept of angular displacement. Okay, delta theta as the change in angular position. Okay. And we have angular velocity. Now this becomes what we call an axial vector. Okay. So remember in vector algebra, there were two types of vectors, polar and axial. So axial vectors are vectors that have to do with rotation about a given axis. And the unit vector of such a vector, an axial vector, the unit vector for that one is along the axis of rotation. So this becomes rate of angular displacement with respect to time into a unit vector. And that unit vector is along the axis. Okay. So d theta by dt is instantaneous rate of change of angular position or displacement with respect to time. But n cap is what we call the axial unit vector. So it is the unit vector along the axis of rotation. And its direction is determined by the right hand thumb rule. That is wrap your right hand fingers along the sense of rotation and your thumb points along the axis. So that right hand thumb rule basically means that if I see anti-clockwise rotation, then my axis is coming out of the plane. So n cap in such a case would be, let's say, k cap if this is my xy plane and the rotation is happening anti-clockwise. But similarly, if the rotation is happening clockwise, then my unit vector would be into the plane. So if I'm talking about, again, in an XYZ system like this, if the rotation looking into the Z axis, the rotation looks clockwise, then my n cap would be minus k cap in this case, going into the plane. So that is the right-handed convention or right-hand thumb rule convention, that when we consider an axial vector looking into that axis, if the rotation looks clockwise, then the unit vector is going into the plane, and if it looks anti-clockwise, then it's coming out of the plane. So this is the same right-handed convention that we use right from the start in vector algebra, from the definition of Cartesian coordinate system XYZ. Okay, the same reason why I cap cross j cap is equal to k cap and not minus k cap, because we are using a right-handed coordinate system and not a left-handed one. So that same convention is continued for the definition of axial unit vectors.
So noted.
Okay. So now in general, when we talk about angular acceleration, it is rate of change of angular velocity.
So just a second.
Yeah.
So below into the plane and coming out, you've written minus k cap and plus k cap, right?
Yes. Okay, so anti-clockwise is plus k cap. And in this diagram, you can see, if I take x-axis horizontal and y-axis vertical like this, then k cap is coming out of the plane. No?
Yes, sir.
So even between I cap, j cap, and k cap, there is that right-handed convention that k cap is defined as I cap cross j cap, or I cap therefore becomes j cap cross k cap, or j cap becomes k cap cross I cap.
So
But
if
for
you're writing
example,
something, I can't see it.
sorry,
If you're writing something, I can't see it.
okay, is it visible to everyone else?
Yes, sir.
Yes,
This
sir.
cross products that I've written, okay. I'll just reshare it, but it should be visible.
Yes, sir, it's visible.
So this is all again to do with the right-handed convention for a coordinate frame. these rules apply because we use right-handed Cartesian coordinate frame. So this convention is a continuation of that. This is again according to the right-handed system. Because your right hand has that property that if you wrap your fingers around an anti-clockwise rotation and look into your hand, the thumb is pointing out towards you, and vice versa. If you wrap your fingers around a clockwise rotation, your thumb is pointing away from you. So left-handed people have to be extra careful that they remember to use their right hand when working out this convention. Anyhow, so in pure rotation, all this doesn't make that much of a difference because the axis is fixed. Okay. Now let's come to the definition of angular acceleration. So the general definition of angular acceleration is that, again, it is an axial vector which is defined as the rate of change, the instantaneous rate of change of angular velocity. So angular acceleration is just defined as the rate of change of angular velocity with respect to time, of course. So the calculus definition will just be given by this formula. Okay. Now, in general, this formula can be a little tricky because if you have a situation where n cap is variable, then the differentiation has to be accordingly. Okay. But in case of pure rotation, it is not a problem at all because n cap is fixed because the axis of rotation is fixed. Okay. So for pure rotation, and at the moment we'll worry only about pure rotation. So for pure rotation, the axis is fixed. So that means n cap is a fixed unit vector. Okay. So that means differentiation of omega with respect to time will just become this. Okay. So alpha can also be written as this or this or even this way. You can say that the magnitude of alpha is d omega by dt. But there are cases where n cap could be changing with time, and that becomes very complicated then. So we will discuss a little later about that when we come to parts ahead of pure rotation, rotational mechanics. But in cases where n cap is time varying, example being a spinning top, which is an example of something in rotational mechanics called a gyroscope. So if you observe a spinning top, generally speaking, the way it's spinning on a surface, it's spinning in such a way that it gyrates. So if this is the axis of rotation about which it is rotating, now this whole axis itself is rotating. So after some time, you see it like this. So this whole thing is going like this. So your n cap itself is in rotational motion. So n cap is actually spinning itself. So in such a case, when we look at alpha, it becomes like d omega by dt n cap plus omega into d n cap by dt. Because n cap itself is spinning. But in pure rotation, of course, we don't have to worry about this. Okay, so this becomes the situations for pure rotation.
So done.
1 second.
Yeah. Okay, done with this now.
Yes, sir.
Okay, so once we've defined the angular parameters in terms of kinematics of pure rotation, now we will also look at the velocity and acceleration of individual particles which are part of the rigid body, because from there only we'll be able to define dynamics. Okay. So acceleration and velocity of an individual particle within a rigid body which is in pure rotation. So how we define these things in terms of the angular parameters? Let's look at that. Okay. So basically it's like now we are talking about the kinematics of a single particle which is part of a larger rigid body, and that rigid body's state of motion is that it is in pure rotation about a fixed axis. I mean, pure rotation means rotation about a fixed axis. So if this is my fixed axis, as if it's like coming out of the plane, so you can see anti-clockwise rotation, and omega and alpha are the instantaneous. So for example, if I also define the plane in which the rotation is happening, if I define that as the xy plane, okay. Now this doesn't mean that the rigid body is laminar. Okay. Rigid body is three-dimensional in general, so it's not necessarily lying in the xy plane. We are seeing the diagram such that we're looking into the xy plane. So my n cap is k cap. Okay, fixed axis which is along the z axis. Okay, and I'm seeing anti-clockwise like this. So now, so accordingly here my omega will be some magnitude into k cap, and alpha will be that same magnitude of alpha into k cap. Okay, because n cap is equal to k cap in this case. I've taken this. Okay, now if I consider any arbitrary particle dm, let's say, and this is lying at a general coordinate xyz. So now remember, for a particle p, the vector r is always defined as the position, not with respect to the origin, but in rotation it is defined as the position with respect to the axis of rotation. Okay, because magnitude of r is the perpendicular distance from the axis. So if the particle has coordinates xyz, so it's not necessarily lying in the plane of, or in the xy plane or the plane of the paper. It can be outside the plane of the paper also, but still what we consider as the position with respect to the axis of rotation will be, in this diagram it will look like this, but actually it is the perpendicular drop from the particle onto the z axis, because here the z axis is the axis of rotation. So this is a vector joining the particle with the z axis, not necessarily with the origin. So that is one thing you have to understand. Okay, so here r will be x I cap plus yj cap. It will not include z k cap because it is defined in this way. Okay. So then you can see that this particular particle, so the particle P is in circular motion about the z-axis, okay, with radius smaller. Okay. So now for its circular motion, r cap will become, like if this angle is theta, cos theta I cap plus sin theta j cap, and theta cap will become minus sin theta I cap plus cos theta j cap, and n cap will therefore become k cap. If you do this, you can see here. So in this diagram, for that particular particle, the radial unit vector is in this direction, and the tangential unit vector is in this direction. So the velocity of that instantaneous velocity of that particle becomes r omega theta cap. So that in terms of the vectors is now defined as omega cross r. It's something that we've seen in circular motion also before. So this is the complete vector algebra up to this situation where we are looking at the velocity of the particle.
So why did we cross r cap and theta cap to get n cap?
Okay, so let's understand how we get this cross product thing. So there is a relationship between these three unit vectors, r cap, theta cap, and n cap. Okay. So if this is the position vector of anything in circular motion about this axis, then the unit vector r cap is like this. Okay, the unit vector theta cap is like this, and the unit vector n cap is coming out of the plane.
Yes, sir.
So they have a relationship that n cap is equal to r cap cross theta cap, and that now works in circularity. Okay, so r cap is equal to theta cap cross n cap, right? And theta cap is n cap cross r cap. So now you'll remember in derivation in circular motion, we had seen how we got the instantaneous velocity. It was rate of change of instantaneous position, right?
Yes, sir.
So it was rate of change of this, which became what? It became r into omega into minus sine theta I cap plus cos theta j cap on
That-
differentiation, right? So it became r omega theta cap. Now we want to express this like this. So if you want to express the relationship between VR and omega, so one thing you can see is that the magnitude of V is r into omega, but you can also see that V is along n cap, V is along theta cap, okay, r is along r cap, and omega is along
n cap.
n cap. So these are three mutually perpendicular vectors, no?
Yes, sir.
So because they are mutually perpendicular and they have this relation, so they are related by cross product. Okay. So when we want to relate them by cross product, what you do here is you just substitute theta cap as this thing, n cap cross r cap. Are you understanding now why it's omega cross r?
Yes, sir.
Okay. So this is something, now you can test it out now in this diagram. If your rotation is happening, so in this particular case, if the rotation is happening anti-clockwise, okay, then your n cap is coming out of the plane.
Yes, sir.
Okay. So now for a position vector r over here, what will be the direction of omega cross r? So point your thumb coming out of the plane, your right hand thumb, and your fingers along r. So where your palm is pointing, it's pointing in this upward sort of direction. No? So you can see the direction of V is like this because V is omega cross R. Okay.
Come
Whereas
along, then
cross product, no beta.
it's a,
The right hand rule for cross product. Now how you apply it? Right hand palm rule, right?
what's right hand palm rule?
Okay. How have you learned cross product before in vector algebra? The direction of cross product, how have you seen that?
So we curl the fingers in the
So you
direction.
do that only, curl the fingers, that's also okay. Okay. So curl your fingers, okay. From which direction to which direction here when we are doing omega cross R?
Sir, I got it.
Got it, no? Okay. Now same thing, suppose it had been clockwise. You'll see the direction it simply reverses. Because now omega is n cap is into the plane. Okay. So if you see a particle which is at position vector R over here, now what will be the direction of omega cross R? You curl your fingers into the plane like that. So V will come like this.
Yes, sir.
Okay. So the cross product gives us not only the magnitude that V is equal to R omega, but it also gives us the direction of V. Okay. Which is the theta cap. So that's why it's important to know it as a cross product. Okay.
Okay, sir.
Okay. So that is about V. Okay. Now let's come to acceleration of that particle. So instantaneous acceleration of that particle is rate of change of velocity with respect to time. So it is R omega theta caps rate of change. Okay. So here R is constant because it has a fixed axis. I mean, it's a rigid body rotating about a fixed axis. So every particle is at a fixed perpendicular distance. Okay. But omega is such that d omega by dt is alpha, and theta cap is such that d theta cap by dt is how much? It is minus omega r cap. Okay. Again, this derivation comes from this, that if you apply chain rule, so if you are feeling little unfamiliar with these things, now just go back to circular motion and see the derivation of these things. We have discussed them. So that becomes minus omega into cos theta I cap plus sin theta j cap. So there is this relationship between these two, okay, that minus sign here. Rate of change of theta cap with respect to time is like this, whereas rate of change of r cap with respect to time is omega theta cap. It comes from a similar derivation. So now when we apply this over here, we can see that the acceleration will become r into d omega by dt theta cap plus omega into d theta cap by dt. So that acceleration becomes r alpha theta cap, okay, minus r omega square r cap, which you are all too aware of. Okay, so this acceleration is a combination of tangential acceleration plus centripetal acceleration, where tangential acceleration is r alpha theta cap and centripetal acceleration is minus r omega square r cap, pointing towards the center. So this is all like, recap of circular motion that you've seen before. But now remember that in context of the pure rotation, it's not just one single particle in circular motion. There are infinite number of such particles. So if we pick up a particular particle which is at a position vector r, then that particular particle has an acceleration which is like this and a velocity which is like this.
So noted.
Okay, noted. Now.
So one second, one second.
Yeah.
Done, sir.
Okay. Okay, now one interesting thing is that even these components of acceleration can be expressed as cross products. The tangential component of acceleration, which we can see is r alpha theta cap. Now, if you see in this, tangential acceleration is along theta cap. Okay, r vector is obviously along r cap, and alpha vector is along n cap. So again, these are three mutually perpendicular vectors. Okay. So you can see that tangential acceleration will be defined as alpha cross r.
So that's just the directions, right? Not the magnitude.
Yes, yes. Okay, so that's why the magnitude is r alpha, because they are mutually perpendicular. No? But this is also showing you the direction, which is important, isn't it?
So we can make this conclusion only when we know, right, that AT is equal to R alpha.
Yes. Okay. And similarly, the centripetal acceleration, which is minus r omega square r cap. So this can also be written as minus v into r. Okay. Into r cap. Sorry, minus v into omega. Into r cap, because v is equal to r omega. So now if you look at centripetal acceleration, instantaneous velocity and instantaneous angular velocity, these are also mutually perpendicular vectors. Okay, because this is along minus r cap, this is along theta cap, and this is along n cap. Okay, so here also there is a relation, cross product relation, that this is omega cross v, and therefore sometimes you will also see this relation. It is omega cross of omega cross r, because v is omega cross r. So these cross product relations also become important sometimes. Okay, so I'm just listing them separately. Cross product relations, they can be used for circular motion also. Okay, so v is equal to omega cross r. Tangential acceleration is equal to alpha cross r, and centripetal acceleration is equal to centripetal acceleration is equal to omega cross v, or that is the same thing as omega cross r. Okay. And of course, the net acceleration is the sum of centripetal plus tangential acceleration. And apart from that, you have these important relations also, that n cap is equal to r cap cross theta cap. So there is that circular relation holding between these. Okay. And then these two relations are also important when you're looking at these derivations. So I'll show you why these vector relations are going to be important in rigid body dynamics. Okay, because you can always have a problem where the quantities given to you in the question are in terms of arbitrary unit vectors in XYZ space. Okay, it's not necessary that you have to have a question where the axis of rotation is the y-axis or the x-axis. It could be lying in the XY plane at some angle, and then you have some particle which is whose coordinates are given to you, and you have to find the velocity or acceleration and all that. So then, working it out manually becomes very difficult, whereas if you know the cross product relations, it's very easy to work out.
Okay, sir. Sir, noted.
Yeah. Okay, so I'll just give you an example. We'll conclude with that for today. So just a pure kinematics type of question. Suppose we have something like this. We have a square plate, okay, which is like this. Okay. Of dimension L by L. Okay, let's say L is equal to some 50 centimeters or something. Now the square plate happens to be rotating about this axis. The square plate is rotating about the diameter axis, sorry, the diagonal axis at an angular speed omega like this, which looks anti-clockwise when you see it from that side. Like the axis of rotation. Now let me name the corners of the square plate. So the axis of rotation, it is rotating at uniform omega. Let's say omega is equal to 2 radians per second about the axis dB. So the unit vector is the unit vector along dB. Okay, so it's pointing from D to B. So from that you can understand the sense of rotation. So now if we define our XYZ system like this. So at the given instant, the square is lying in the XY plane as shown. Okay. Of course, it's not going to always lie in the XY plane because it's rotating about this axis. So at the instant when the plate is in the XY plane as shown, okay, find the instantaneous velocity and instantaneous acceleration for a particle P, which is now shown over here. Okay, so this particle is on this side at a distance L by 3 from this end. So very specific question you can see. Okay. And even before that, let's do one more part of the question where write the angular velocity in vector form. Okay, taking this system of XY plane. So this will show you part of the application of the above concepts. Okay, part of the application here, because of course there's no alpha, it's rotating uniformly at omega. So just try this out, people. Okay, so now see this question we can do both ways. We can just do it geometrically by just understanding magnitude and direction and all this in the diagram itself, or we can do it using vector algebra. Okay. But you can imagine that if we have, for example, a three-dimensional version of this type of question, like instead of the square, it is a cube or something, then it's not going to be so easy. Okay. Working it out manually. So that is where the vector algebra thing becomes important. Okay. So this is a square body, and this is our axis of rotation. So now we are considering this point P over here, where this distance is L by 3. Okay, then what in this diagram, which is the position vector of that particular particle with respect to the axis of rotation? It will be this. From here we have to drop the perpendicular. Okay.
Yes, sir.
So this is still relatively simple geometrically, because after all you are dealing with simple isosceles right angle triangle. You can see that the magnitude of R will become L by 3 root 2. Okay. So now you can see that omega is such that it's anti-clockwise from this side. No? It's like this. So this point is basically coming out of the plane at the moment. Okay. And this point is going into the plane. So this point P will have a velocity coming out of the plane.
Yes, sir.
Okay. So the velocity of the point P will be R omega. So that is L omega by 3 root 2. And the direction will be coming out. So the velocity we can then express as a vector k cap, because we've taken x and y system like this. Okay. Now we can also see that as far as acceleration of the particle is concerned, it has only centripetal acceleration. The tangential acceleration is 0. So the centripetal acceleration will have a magnitude of, okay, so this much. Okay. And the direction,
Along minus r cap.
yes, will be minus r cap. Now you can see that r in my diagram is along this sort of direction. R vector is like this.
Yes, sir.
So r cap is minus 1 by root 2 I cap plus 1 by root 2 j cap. So the acceleration vector of that particle will become this into I cap by root 2 minus j cap by root 2. Or we can simplify this further, and so L omega square by 6 I cap minus j cap. So that is the acceleration of this particle. Or we can use the cross product method. So if we use the cross product method, you can see that R vector is L by 3 in magnitude, and the direction is r cap. So it is L by 3 root 2 minus I cap plus j cap. Okay. And omega vector is omega n cap. Okay. And in this case, this is the direction of n cap. So that is omega into 1 by root 2 I cap plus j cap. Okay. So this n cap will be this. So now you can see that you can get velocity as omega cross r.
Sir, how did we get r is equal to L by 3 r cap?
L by 3 root 2.
No, sir, L by 3 r cap. How
No,
did we
sorry,
get
it is
that?
L by 3 root 2. My mistake. There is.
Yes, sir.
Okay. So that will work out to this. And it will work out to this. So you can work out the cross products using the 2 by 2 matrix and all that also. Okay, but it will be easy enough to show that this will work out to this and this will work out to this. So now you can imagine in a more complex three-dimensional system, instead of this square, if I had a cube and I had one of the body diagonals as the axis and all that, it would not be so easy to work out the directions manually and all that, whereas it would be quite simple to work it out in this manner, right?
Yes, sir.
Okay, so that is why those cross product relations are important. So we'll conclude today's session here, and next lecture we will look at some additional aspects of moment of inertia, and we will also look at the concept of torque, and that is where dynamics of your rotation will begin, the relationship between torque and angular acceleration, and there we'll see the other application of moment of inertia.
Sir,
So that's it. Yeah.
oh, I forgot my doubt.
Sir, can you send the system of particles module answer key?
Yes, I will be sending the answer key very soon. Okay, you'll have to verify the answer key because it's been prepared in a hurry, but I'll send it very soon. Okay.
Okay, sir.
Thank you.
Okay, that's
Bye,
it
sir.
for
Thank you,
today's
sir.
session, people. Wish you all the best.